Okay, so we've talked about the multiplication principle, the addition principle. Multiplication principle is if you have a sequence of choices, you multiply the number of choices at each step. The addition principle is if you have different cases, you add up the number of things in different cases, always being careful about the overlap between cases. So permutations is something that's related to the multiplication principle. So permutation of n distinct objects is an ordering of the n objects, and our permutation of n distinct objects is an ordering of n out of n. So that's the definition. How does it actually work? How many different orderings of these 5 letters are there? Well, an ordering means I'm not repeating them. 1, 2, 3, 4, 5 spades with no repeats. So to put them in a particular order means first this one, then that one, then the other one, then the other one. So I don't have any repeats. So how many possibilities are for the first letter? 5, 4, 3, 2, 1. And 5 times 4 times 3, 2, 1 is 20, 60, 120. 120 possible different orderings of those. How many different orderings have both the substrings BC and DE? Well, we have to consider some cases for that. Right? Basically, this is the question is where does A go? And A can go in a lot of different places. But you could have BC and DE like this and put A at the front. Or you could have BC here and then DE there, put the A in the middle. Or you could have BC and then DE and put the A at the end. Right? So that's 3 possibilities. But there's 3 more possibilities because we could flip the DE and the BC. That. So there's actually 6 different cases for where you can put the A because it depends on which order you put the BC and the DE in. So 6. Either the B string, substring BC or the substring CD. Well, the substring BC again, there's a couple different cases. You can put the BC at the front and then put in 3 more there. Or you can put the BC in the second spot and have 2 afterwards. You can have 2 letters, then the BC, and then the BC at the end. Or you can have 3 letters and the BC at the end. So how many choices do you have for each one? 3 choices here times 2 times 1. So 6, 6, 6, 6, 24 cases for BC. So, okay. So 24 strings have BC in them. 24 cases strings, same analysis, gives you CD. 2 different cases. What do you have to be careful about when you're doing those cases? What's the overlap? How many strings have both BC and CD? Well, since they overlap, that means you can do BCD and then 2 more, or you could have another case, BCD and then 2 more, or 2 and BCD, like that. So BC and CD, you can have 2 choices, 1, so there's 2, 4, 6 cases there. So how many possible are there? 24 strings have BC, 24 strings have CD, 6 strings have both. And so that's 48 minus 6. There's 42 strings that would have either BC or CD. So you have to think about cases a little bit and thinking about these orderings of things. How many different suborderings of 3 of these letters since I've run out of space? And I don't know why C and D are backwards there. I have 5 choices for the first, 4 choices, 3 choices, 20, 60 choices for choosing 3 out of 4. So that would be a 3 permutation of 5 distinct objects. There's 60 of those. Taking all 5 with no repeats, That gives me 120. So generalize these examples to come up with some formulas for the number of permutations. But before we do that, we can talk about some notation. Factorial, and factorial is this, n times n minus 1 times n minus 2 times dot, 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 3 times 2 times 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. That's 120. That shows up naturally in the multiplication principle if you're thinking about no repeats. 5 factorial divided by 2 factorial, 5 times 4 times 3 times 2 times 1 over 2 times 1. Those cancel out. 5 times 4 times 3. That's the number of three permutation of 5 things. So that's my 1022 factorial over 1020 factorial. Your calculator will choke on both those numbers, but it's easy to calculate what the ratio of these two is. But now I'm going to run out of space. So we're just putting a lot of dot, dot, dots. So 1022 factorial is 1022 times 1021 times 1020 times 1019 times dot, 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 all the way to 1. 1020 factorial is 1020 times 1019 times 1018 times dot, 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 all the way down to 1. This whole part canceled that whole part. So this is 1022 times 1021. Right? So 1022 factorial divided by 1020 factorial is 1021 times 1022. 5 factorial divided by 2 factorial. Start counting from there. 3 times 4 times 5. So let n and r be positive integers. The number of r permutations is this, p n r, which is n factorial over r factorial. So if I have n things, if I'm choosing r things out of n in no particular order, right, I have r spaces, put n here. If I'm having no repeats, then n minus 1 there, n minus 2, n minus 3, dot, 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 down to n minus r plus 1. You multiply all that out, that becomes n factorial over n minus r factorial. So 5 times 4 times 3, right? That's 5 factorial divided by 2 factorial. So this just comes straight from the multiplication principle, right? You multiply down to a certain point and you terminate it. Combinations are similar to permutations, but I'm not worried about the order. So a combination of r objects taken from a set of n distinct objects is just a subset of size r from the entire set of n objects. So if we're looking at the letters A, B, C, D, E, how many 3-element subsets are there? You could have A, B, and C. You could have A, B, and D. You could have A, B, and E. Those are all the subsets that have A and B in them. Then you could say, well, what are the subsets with A and C, A, C, D, and A, C, E? What are the subsets with A and D, A, D, E? So these are all the subsets with A in them. What are the subsets that have B in them but don't have A? Well, you could have B, C, D, B, C, E, or B, D, E. And the last one is C, D, E. So there's 10 subsets. Note that each one of these can be ordered in 6 different ways. Right, so CDE, that could be ordered as CDE, as CED, as DCE, as ECD, as, let's see, now we start with, put the C at the back, DEC, and EDC. So there's the 6 orderings. So how are permutations and combinations related to each other? So if we want to build a permutation, we can do it in a 2-step process. One is pick r things from n. So suppose we take 3 out of 5, like CDE, and then we order those. Right? And so there's 6 ways to order a 3-element subset. So r factorial. So the number of permutations, to get a permutation, what do is pick 3 letters and then put them in a particular order, 2-step process. So number of subsets times number of ways to order the subsets. number of subsets times number of ordered ways subsets gives me PNR, and then that gives me the formula n factorial of R factorial. N factorial over R factorial times n minus R quantity factorial is the number of combinations. Okay, so the formulas aren't super important because your calculator, computer, whatever you're using can do that for you. So Jovians are aliens from Jupiter. Martians are aliens from Mars. They get together at a conference. There's 35 total. How many different subcommittees of 10 aliens are there? Right? Not worried about particular orders here, right? So I'm just going to take 10 out of 35, right, randomly, and see 3510, whatever number that is, you can calculate it. That's your number of possible subcommittees. It's actually quite a lot. Oh, I did actually write that one down. 1,835,79396. 183,579,396. So it's quite a lot. So if you choose 10 aliens from 35, you have that. So if we have one of these subcommittees and we want to be able to choose a chair and a note taker, a chair alien and a note taker, how many ways are to do that? Here, order matters, right? If you pick a Jovian to be the chair and a Martian to be the note taker, that's a different choice than choosing the same Jovian to be the note taker and the same Martian to be the chair. So you have, out of 10 aliens on your subcommittee, you have 10 choices for the first one and 9 choices for the second. So there's 90 possible ways to pick a chair, alien, and a note taker for the committee. And here the order matters, right? Because who does what is that matters. But if we're not worried about how many there are, what the orders are, then we don't have to include that. Oh, and I screwed the notes here too. Okay, so there should be a C, obviously. How many subcommittees of 10 aliens are only Jovians? Well, there's only 20 Jovians. So see 2010, right? Choose 20 from 10 from 20 because there's only 20 Jovians. How many have exactly one Martian and 9 Jovians on them? Well, here I have to choose ABC, choose one Martian from 15, and then choose 9 Jovians from 20, right? It's a sequence, right? Multiplication, and then means multiplication. So I have to choose C15-1 times C29. 1 out of 15 Martians, and then choose 9 out of 20 Jovians. And that'll give me a subcommittee of exactly 1 Martian and 9 Jovians. Likewise, either 2 or 3 Martians, exactly 2. That's exactly 2. 2 out of 15, and then 8 out of 20. Note that 2 plus 8, that's my 10 people on the committee, 8 Jovians, 2 Martians, or as a plus, right? That's addition principle. C15-3 times C27. That's exactly 3. So how many subcommittees have 4 or more Martians? This is a complement, right? If you see 4 or more, 4 at least 4, whatever. If you think about all the possible subcommittees, you can have subcommittees that have no Martians, subcommittees that have 1 Martian, subcommittees that have 2 or 3 Martians, and then subcommittees that have 4 or more Martians. So the sum of these is that. right? All your committees either have no Martians, one Martian, 2 or 3 Martians, 4 more Martians. So what's the answer to this one? Well, we know the answer to this question, minus the answer to this one, minus the answer to that one, minus the answer to that one. That'll give us the answer for the last one. So suppose a company has retail outlets in St. Cloud that's got 12 employees, Wake Park with 15, St. Joseph with 7. They're going to open a new store in Sartell, transfer 3 employees from St. Cloud, 4 from Wake Park, and 2 from St. Joseph. How many ways can they do this? So there's going to be a sequence of things here. They're going to transfer people from St. Cloud, and then they'll transfer people from Wake Park, and then they'll transfer people from St. Joseph. Right? So it's a sequence. It means you're going to multiply things together. Multiplication principle. How many ways are there to pick 3 people out of 12? Well, that's what a combination does. If you're just picking 3 people at random out of 12 and not worried about what order you pick them in or anything, it's C12-3. New store in Wake Park, they're going to take from 12, they're going to take 4. And then, oh, Wake Park has 15. And then from St. Joseph, they've got 7, but they're going to take 2, so C17. Multiply those together, and that tells you all the different ways that they can take these 9 people out of their employee staff and transfer them to Sartell. Okay, and finally, this is another complement problem. Right, 100 cameras, 7 of which don't work. Right, so we have 100 cameras, 93 are good, 7 are bad. Okay. Selections of 10 cameras. C110. How many selections of 10 working cameras? Well, we just take C9310. Right? We have 93 working cameras. We can pick 10 of those. How many selections of 10 cameras include at least 1 non-working camera? Okay, so at least 1 non-working camera. Again, we're going to break this up into cases. If you think about selections of 10 cameras, there's 2 types of selections you can make. You can make ones that are all good cameras, or ones where a selection of 10 where some of them are bad. We know how many selections of 10 there are. C110. We know how many contain no non-working ones. That's picking 10 good ones out of 93. So C100, 10 minus C93, 10. That gives you the number that have 1 or more non-working. And we can do the same thing, at least 2 non-working cameras. Well, all selections of 10. It's a set, and we can break it up into 10 good, 0 bad, union 9 good, 1 bad, union 8 or fewer good, and 2 or more bad. So all my selections of 10, either they're all good, or I've got 1 bad and 9 good, or I've got 2 or more that are bad and 8 or less that are good. And I want to know how many cases there are of this. But I know how many cases there are of this. This is C110. I know how many cases there are of this. That was my C9310. I know how many cases there are of this. That was this, which doesn't actually help, but I can calculate this. This is picking 9 good ones, then picking 1 bad one, right? 9 out of 93 good ones, and then 1 out of 7 bad ones, and then plus however many of these are. So I know this, I know this, I know this. So I can figure out this by taking this minus this minus this. So it complements again.